this lecture, we will perform Silvaco TCAD simulation of light emitting diodes. So let us start the deck build interface for Silvaco TCAD for that purpose. This is the window for Silvaco TCAD software, and I'm going to open a file which I already saved for the light emitting diode structure. This is the code that I have prepared. We will talk about the code in a bit, but before that, I want to give a slight overview of some of the basic concepts of light emitting diode. We have discussed it in detail, but I want to talk about just a few concepts. So a light emitting diode is a semiconductor device in which the input is electrical and the output is optical. The input is voltage, resulting in current flow through the light emitting diode structure. In the light emitting diode, we have diffusion of carriers, diffusion of electrons and holes, and these electrons and holes recombine, resulting in the emission of light corresponding to the band gap of the semiconductor. The emission wavelength corresponds to the band gap of the semiconductor. Then there are different light emitting diode configurations. The simplest one is a PN junction. Here is a PN junction under thermal equilibrium. Under thermal equilibrium, we know that there is a barrier for carriers to cross over. There is a built-in potential barrier, so electrons cannot cross this barrier to flow to the p-side layer, and similarly there is a barrier for holes to cross to the n-type layer. However, under the application of a forward bias voltage, we actually drag down the p-side of the energy band we actually drag down the energy levels on the p-side of the semiconductor, reducing this barrier, allowing for carriers to cross over into the other layer. So electrons can now easily flow from the n-type layer to the p-type layer, and similarly holes can now easily flow from the p-type layer to the n-type layer. Over here around the depletion region, they come across each other, so they get an opportunity to recombine, resulting in the emission of light corresponding to the band gap of the semiconductor. This is a basic configuration of a light emitting diode. Here we have a few number of carriers, few number of electrons and holes which get the opportunity to recombine, resulting in the emission of light. So since we don't have high concentration of carriers to recombine, this kind of basic PN configuration light emitting diode structure would result in low intensity light. We would not have enough visible light for our purpose of interest. So we need to actually work on more complicated structures in order to achieve high intensity light. For that purpose, one structure that can be used is double heterostructure N plus P LEDs. In this structure, we have a narrow bandgap material, for example, gallium arsenide, which has a bandgap of 1.4 electron volts. And this narrow bandgap material is sandwiched by two wide bandgap materials on either side. For example, aluminum gallium arsenide on the right side and aluminum gallium arsenide on the left side. and these two materials have a band gap of 2 electron volts. Now, under thermal equilibrium, the holes can easily flow into this narrow band gap layer, which is the active layer, the light emitting layer, but there is a big barrier for electrons to flow into this active region. However, under the application of a forward bias voltage, what happens is that this barrier is reduced, and now electrons also get an opportunity to flow into this active region. We have a huge concentration of electrons and holes across the band gap of the semiconductor in the conduction band and valence band. They get an opportunity to recombine, resulting in emission of light. And then we can work on more advanced structure as well. For example, here is an example of a gallium nitride based light emitting diode structure, in which we have an n-type layer at the bottom, which is grown on top of a sapphire substrate, and then at the top we have a p-type gallium nitride layer having a certain hole concentration. In between we have an active region, resulting in the this active region is actually the light emitting region. The light emitting region for gallium nitride based LED is composed up of indium gallium nitride material. Now, why indium gallium nitride? Why not gallium nitride when we are talking about gallium nitride based LEDs? Because the band gap of gallium nitride is 3.4 electron volts. So the corresponding wavelength becomes, according to the simple formula, E is equal to Hc divided by lambda, or lambda is equal to Hc divided by the band gap of the semiconductor. And simplifying it, it reduces to our wavelength of emission is equal to 1240 nanometers divided by the band gap of the semiconductor. For gallium nitride, the band gap is 3.4 electron volts. So its corresponding wavelength becomes 365 nanometers, which is in the ultraviolet range. However, for the visible light range, our wavelength of interest are in the range of 400 nanometers for bluish kind of light, and 750 nanometers for red light. And in between we have green, yellow, orange light as well. So we need to find a material which has a band gap corresponding to the visible wavelength range. Now, another material is indium nitride, which has a band gap of approximately 0.7 electron volts, but its corresponding wavelength is in the range of infrared light. So we actually make an alloy of indium nitride with gallium nitride, which gives us the flexibility of tuning the band gap of this semiconductor in the range of 0.7 to 3.4 electron volts. 0.7 for indium nitride and 3.4 electron volts for gallium nitride. For example, consider 10% indium and 90%, consider 10% indium and 9% gallium nitride. So this corresponds to a wavelength in the close to the ultraviolet light range, around 420-ish nanometers. If we increase the indium content to 20%, then it's going to give us wavelength in the blue light range, around 450 nanometers, 460 nanometers, in that kind of range. If we further increase the indium content in the indium gallium nitride alloy to around 30%, then the corresponding band gap and the band gap leading to a particular wavelength would be around in the greenish light range. And similarly, we can achieve up to a maximum of 40% indium content in terms of the growth. I mean, there are some groups, for example, the group of Dr. William Allen Doolittle from Georgia Institute of Technology. they are able to achieve indium gallium nitride in the entire alloy range, but a lot of people are only able to achieve up 40% indium gallium nitride. So 40% indium gallium nitride, 40% indium, 60% gallium nitride would result in wavelength corresponding to green or yellowish kind of light. So we actually have control over the wavelength of light if we adjust the indium content of the indium gallium nitride material. And here in this structure, we actually have two active layers, but in the structure that I'm going to simulate, we do not have two active layers. We just have one active layer. So now let me switch to the simulation. Over here, I already opened the code, so let me run the simulation and here is our layer structure diagram. In this layer structure diagram, this blue layer actually is sapphire, ranging from 0 to 350 micrometers in the x direction and from 4 to 10 micrometers in the y direction. And actually in Silvaco TCAD, the x direction in the towards the right is the positive x-axis, and similarly the y direction is positive downwards. So our sapphire layer is in the range of 4 micrometers to 10 micrometers in the y direction and 0 to 350 micrometers in the x direction. This layer over here running along these edges is our n-type gallium nitride, which starts from approximately, I would say, I need to zoom in on this, 603 nanometers or 0.603 nanometers to 4 micrometers over here, and similarly from in the y direction, and similarly from 0.603 micrometers to 2 micrometers over here in the y direction. And along the x direction, the dimensions up to this point are from 0 to 185 micrometers for the n-type gallium nitride layer. And this layer also extends further to the right. So the dimensions over here are from 2 micrometers to 4 micrometers in the y direction, and from 185 micrometers to 350 micrometers in the x direction. So I call this my layer number 1 in the Silvaco TCAD code. This is n-type gallium nitride. And then on top of the indium gallium nitride, in this layer structure diagram, once again I'm going to zoom in on this region. For zooming in, I need to press I need to left click and I need to hold it, and then I need to make a rectangle around that region. So you might see this really thin purple layer. This is actually our indium gallium nitride layer, which is super thin in the y direction. Its thickness is in the range of 0.6 micrometers to 0.603 micrometers. So the thickness of this layer is 3 nanometers. It's really thin, and there are actually scientific reasons for that. So what happens is, in terms of growth, we have spontaneous polarization because we need to grow these materials on heterogeneously on top of different kind of materials. And because of that, there is a lattice strain involved in this layer, leading to spontaneous polarization. And then for light emitting diode, we need to apply voltage to it, resulting in current flow through this light emitting diode, and that results in piezoelectric polarization. And the combination of piezoelectric and spontaneous polarization actually results in band bending in the energy band diagram. And we are actually going to see the band bending later when I show you the energy band diagram for this structure. So this layer over here, extending from 0.6 micrometer to 0.603 micrometer, is our Indium gallium nitride layer. It has a 3 nanometer thickness, and in the x direction it extends from 0 to 100, and once again let me zoom in on this point so that you can actually see. In x direction it extends up to 185 micrometers. For zooming out, I need to click over here, like in the center of this icon, in order to zoom out on this structure. And then on top of the indium gallium nitride layer, I'm actually growing another layer, which is, I need to zoom out once again and zoom in on this layer. Okay, so on top of the indium gallium nitride layer, I'm growing another layer which is aluminum gallium nitride, running from 0.5 micrometers to 0.6 micrometers. So it has a thickness of 100 nanometers, and it's running from 0 to 185 micrometers in the x direction. The aluminum gallium nitride layer, and we have color codes over here as well for these layers. As you can see, aluminum gallium nitride is the pink layer. Aluminum gallium nitride in this structure is called the electron blocking layer, and we will try to understand that concept later from the energy band diagram. On top of the aluminum gallium nitride layer, this layer over here running from 0 to 0.5 micrometers. From 0 to 0.5 micrometers, this is the p-type gallium nitride layer. It has a thickness of 0.5 micrometers in the y direction, and in the x direction it's running from 0 to 185 micrometers. And then finally we have the p-type contact and we have the n-type contact. So this is the basic description of these layers. Now let me get back to the code. So from this layer structure diagram, we see that and for the contacts, actually the contacts are running from the p-type contact is running from -0.1 to 0 in the y direction, so it has a thickness of 100 nanometers, and in the x direction it's running from around 15 micrometers to 175 micrometers. Similarly, the n-type contact it has a thickness of 100 nanometers or 0.1 micrometers once again, and it's running from 195 to 345 micrometers in the x direction. So our work area for this structure is from 0 to 350 micrometers in the x direction, and from -0.1 to 10 micrometers in the y direction. Inside the code, we first enter the command go device edit. Device edit is a module of Silvaco TCAD in which we can construct the layer structure diagram of any kind of device. And then we define our work area. Our work area runs from 0 to 350 micrometers, as I already told you, I've already shown you over here. It runs from 0 to 350 micrometers in the x direction. But why do we see 3.5 over here? It's not 350, 3.5. Because I've actually included a scaling factor of 100 along the x direction. But along the y direction, my scaling factor is 1. So any value that you see over here in this code for the x direction has a scaling factor of 100. So 3.5 over here actually means 350 micrometers. So my work area is running from 0 to 350 micrometers in the x direction. Similarly, in y direction, I have already shown you in the layer structure diagram. It runs from minus 0.1 to 10 micrometers. Then we define our region number 1, which is this region over here in the layer structure diagram, and it's n-type gallium nitride. So first we define the x and y coordinates for this n-type gallium nitride, and then we'll define the doping for this layer. For that purpose, our coordinates are like, you can start from any point in this layer structure diagram. You can start from here and then follow along the perimeter of this entire n-type gallium nitride region. Or you can have this starting point and then you follow all the edges of this n-type gallium nitride region. But our starting point is from here in this code. So as you can see over here, the x coordinate is 1.85, or as I already told you, the scaling factor is 100, so it's actually 185. And our y parameter is 2. Y coordinate is 2. So our coordinates are 185, 2. This point over here, as you can see, 185 in the x direction and 2 in the y direction. And then it's 195, 2. So this point over here. And then it's 345, 2. This point. 350, 2. This edge, corner. 350, 4. This corner. 0, 4. This corner, 0, 0.603, x coordinate is 0 and the y coordinate is 0.603, as you can see over here, the y coordinate is 0.603. And then 1.85, 0.603. 1.85 is the x coordinate, and so 185 is the x coordinate, and 0.603 is the y coordinate. So we have defined the coordinates, all the coordinates for the n-type gallium nitride region. Now we need to define the doping for the n-type gallium nitride region. The doping is, and we have labeled this region as region number 1. So this region is our region number 1. The impurities are donors, and its carrier electron concentration is 1 into 10 to the power of 18 per centimeter cube for this n-type gallium nitride region. Then we define our region number 2. Let me zoom in on the indium gallium nitride region. This is a really thin region, so I have to zoom in on it a couple of times, or maybe one more time as well. And you can see in the color code as well, it's indium gallium nitride layer, running from 0 to 185 micrometers in the x direction and from 0.6 to 0.603 in the y direction. So then we define the coordinates, all the coordinates for the indium gallium nitride layer as well. You can start from any point. We basically have 4 points for the indium gallium nitride regions, all the 4 corners. So define the coordinates for these 4 points, and after that, so we define the coordinates, and then after that, we need to define the indium content in the indium gallium nitride alloy, because the indium gallium nitride layer is actually the active layer in this structure, as I already mentioned. It's the light emitting layer, and the emission wavelength depends on the percentage of indium content in this alloy. So in this case, I've set the indium content to 0.1, which means we have 10% indium and 90% gallium in this indium gallium nitride alloy. So the indium gallium nitride layer is our region number 2, and then we need to define coordinates for the aluminum gallium nitride layer, which is the pink layer over here, running from 0.5 to 0.6 in the y direction, and from 0 to 185 micrometers in the y direction. So we define the coordinates for this region, and then we dope it p-type. The impurities are acceptors, and the whole concentration is 1 into 10 to the power of 19 per centimeter cube. This seems to be a really high whole concentration for gallium nitride and also for aluminum gallium nitride, but actually one of the best groups in the world in terms of dopings of nitride materials, Dr. William Allen Doolitle's group from Georgia Institute of Technology, they have actually achieved these level of dopings. So it's not a big research issue anymore. We can achieve high whole concentration in nitride materials now. So the whole concentration of this aluminum gallium nitride layer, which is region number 3, is 1 into 10 to the power of 19 per centimeter cube. And then this region is our p-type gallium nitride region, and I label it as region number 4. But before that, I need to, aluminum gallium nitride is also an alloy. We can tune the band gap of aluminum gallium nitride from 3.4, which is the band gap for gallium nitride, to 6.2, which is the band gap of aluminum nitride. So in this case, the aluminum content is 20%. The band gap is higher than 3.4, but it's kind of closer to the band gap of the gallium nitride material. And this layer is called the electron blocking layer. Once again, I'm going to explain this concept a little bit later. Now, our region number 4 is gallium nitride. This p-type gallium nitride layer running from 0 to 185 micrometers in the x direction, and from 0 to 0.5 micrometers in the y direction. So it has a thickness of 0.5 micrometers. We define the coordinates for this layer, and then we set the whole concentration for this layer to 1 into 10 to the power of 19 per centimeter cube. And then our region number 5 is anode, nickel. This layer over here is our region number 5. We define the coordinates for this layer. This is our anode because this is deposited on the p-type gallium nitride layer. In the material I've defined as nickel. However, I have not set any work function for this material, so we assume that it's actually an ideal contact. Region number 6 is cathode. Material is tin. This is our anode, and the material is tin, as you can see from the color codings as well. And once again, I have not set any work function for this material, so I assume that it's an ideal, it makes an ideal contact. Our region number 7 is sapphire, the blue, navy blue region over here, running from 4 to 10 micrometers in the y direction and from 0 to 350 micrometers in the x direction. This is the substrate for the growth of gallium nitride on top of it. Gallium nitride is grown on different kind of substrates. It can be grown on sapphire, it can be grown on silicon carbide, it can be grown on silicon, sapphire has a lattice mismatch of around 16% with gallium nitride. But it's actually a cheaper solution for growing gallium nitride on top of it. Now, after constructing the layer structure diagram, we need to define meshing for this structure. And in order to see the meshing, we need to right click on this structure and then left click on display and click on this icon, click apply and hit OK. So now we see the meshing. What is meshing? Meshing are actually horizontal and vertical lines on this structure, and the intersecting points of these lines is called nodes. So in Silvaco TCAD we can define a maximum of 20,000 points for our particular structure. Defining more number of points would actually result in more accurate simulation of the structure. So what happens at the nodes? At the nodes, we actually apply all the models that we have included in our code, in our Silvaco TCAD code. Shockley red hull recombination, OJ recombination, radiative recombination models, and a lot of other K-Wound model and a lot of other models. So if you include more number of nodes, the limit is 20,000, the simulation time would be longer. However, if you include fewer node points, then the results would be less accurate. So it's kind of like a precious resource that we need to carefully utilize, and because of that reason, what we do is we define denser meshing in the regions which are critical to us. For example, here in this structure, the active region, which is the light emitting region, the indium gallium nitride layer, is critical. So we define denser meshing in the indium gallium nitride layer. Similarly, we define denser meshing for all the interfaces. Here we have aluminum gallium nitride layer. We have an interface of aluminum gallium nitride with the p-type gallium nitride. Another interface of aluminum gallium nitride with the indium gallium nitride layer. And then we have an interface with indium gallium nitride with the n-type gallium nitride. So since here we have a lot of interfaces, we define denser meshing in this region. Similarly, we define denser meshing along the edges and at other interfaces, at the contacts and at other interfaces as well. But we define less dense meshing in the regions which are less critical to us. Going back to the code, here we define the XY coordinates for the meshing, and then we define the spacing for the meshing. Like for example, our light emitting region or the active layer is indium gallium nitride layer running from 0.6 to 0.603 micrometers. So over here we define denser meshing or smaller spacings for the meshing for it. For example, here from 0.599 to 0.604 in the y direction, we have defined the spacing is smaller, so the meshing is denser. And then we save this structure. After defining the parameters for constructing the layer structure diagram, we need to perform electrical simulation. We need to look at the IV characteristics and the power spectral distribution of the light emitting diode. So for looking at the electrical characteristics of the light emitting diode structure, we need to work in the Atlas module of Silvaco TCAD. So that's why we enter the command of go Atlas, and all these pound signs that you see over here, the hash signs over here, are actually for introducing comments into our code. So I'm gonna skip that part. And then for different regions, we set them to different parameters, and we introduce models. We define the Indium gallium nitride layer as a quantum well layer, since this is a really thin layer, 3 nanometers. And then we introduce strain and polarizations in this layer. And similarly, we will have strain and polarization in the aluminum gallium nitride layer as well. Then we define other parameters for gallium nitride, aluminum gallium nitride, indium gallium nitride. For example, we define the electrons and holes recombination lifetimes for these layers. And after that, we introduce different models into our code. The KP model, Fermi model, incomplete recombination model, Shockley red hole recombination model, OJ recombination model, optical models, KP model, Chuang model. Chuang model is actually used for LEDs, and then spontaneous polarization and piezoelectric polarizations, etc. So we introduce different models. We set the mobility of the p-type layer to 10 centimeters square per volt second, because we know that for gallium nitride, the whole mobility is way lower as compared to the electron mobility. And after that, in the layer structure diagram, we want to look at different energy levels. For example, the conduction energy level, the valence energy level, the electric field, electron and hole mobilities, the current flow lines. So we introduce different commands for this purpose. A really useful command over here is band.temp, because it gives us the conduction energy level, valence energy level, and a lot of other parameters as well. And then we save the file, and for plotting the layer structure diagram or any other IV characteristics, etc., we actually use the command of tonyplot. So this point actually gives us the layer. It plots the layer structure diagram for the light emitting diode structure, and I already mentioned meshing, so I'm going to disable the meshing. And I'm more interested in looking at the energy band diagram, especially around the active region. So I want to zoom in on the active region, and for that purpose, as I will tell you, left click, hold it, draw a rectangle around the region of interest, and then just release it. So this is our region of interest. This is our p-type gallium nitride layer, aluminum gallium nitride layer, indium gallium nitride layer, the active layer, and then the n-type gallium nitride layer. In order to probe any region, we actually need to draw a line across this region. So we left click on tools and then click on cut line, draw a line over here, and then release it, left click in this region. Currently they're showing us the dopings in different regions, but I'm more interested in looking at the energy band diagram. So for the energy band diagram, we look at the conduction energy level and the valence energy level and the Fermi energy level, the electron quasi-Fermi energy level and whole quasi-Fermi energy level. The Fermi energy levels are constant for under thermal equilibrium. Also, we see like these aesthetic kind of things, so I'm going to disable them. And we also see these interfaces, like to the left of this line we have the p-type gallium nitride region, and you can confirm it from the energy band gap as well. This is the conduction energy level, this is the valence energy level. So the difference between these two over here is around 3.4 electron volts. So this is our p-type, and then the Fermi energy level is closer to the valence band. So this is our p-type gallium nitride there. From this line to this line over here, we have our aluminum gallium nitride level. And as you can see over here, the band gap slightly increases. Let me confirm the band gap for an aluminum content of 20%. So it starts from approximately minus 0.1, and then it goes up to 3.6. So the band gap for 20% aluminum and 8% gallium, aluminum gallium nitride, is 3.7 electron volts. And then over here, in this region, we have, between these two lines, we have our indium gallium nitride there. And to the right of it, we have the n-type gallium nitride there. As you can confirm it from here, that our Fermi energy level is now close to the conduction band. So now that we have identified different regions, I'm going to disappear these black lines with the help of magic, and that magic is just click on this icon, and this is going to disable it. Right. So now here is our energy band diagram once again. As I already discussed, that this is our electron blocking layer. Now let us zoom in on the active layer, on the indium gallium nitride layer. Zoom out once again, and then zoom in once again in this region. Actually, my meshing spacing over here is approximately is 1 nanometer, and the entire layer is 3 nanometers. I should have done like 5 angstrom, but that should be fine. You can still understand the characteristics, you can still get an idea. So here is our indium gallium nitride layer. It actually forms a quantum well over here, which is not really obvious from the thermal equilibrium, but it's going to be more obvious when we look at it under a certain voltage. So this is the valence energy level for the indium gallium nitride, and this is the conduction energy level for the indium gallium nitride layer. Now, for this structure, as you can see that there is under thermal equilibrium, there is a barrier for electrons to flow into the into the quantum well of the indium gallium nitride layer, and similarly there is a barrier for holes as well, because holes, electrons, they settle at the minimum of the conduction energy levels, and holes try to move to the top of the valence energy level, just like bubbles in water. So there is barrier for both electrons and holes to move into this quantum well. So what we need to do is we need to apply voltage to this structure to enable to lower the energy levels on the p side of the semiconductor, providing smaller barrier for electrons and holes to move into the quantum well. Okay. So let me get back to the code once again. We have looked at the layer structure diagram of the light emitting diode under thermal equilibrium, and now let me walk you through the rest of the code. So we actually introduced probes in the structure from 0.6 to 0.603 in the y direction because this is our active layer. So we introduce a radiative probe in this region, and then recombination occurs in the entire structure, and then we apply a bias to the light emitting diode structure, apply positive potential to the anode and negative potential to the cathode. We ramp up the bias voltage from 0 to 3.5 at a step of 0.1. So it's going to increase like 0 from 0 to 0.1, 0.2, 0.3 and so on. And then from 3.5 to 4 at a step of 0.1, and then from 4 to 4.5 at a step of 0.1. And then we look at the power spectral distribution of the light emitting diode structure in the range of 0.4 to 0.55 micrometers, from 400 to 550 nanometers, because we are adjusting our indium content. In this case is 10%. So the emission wavelength would be close to 400. So, and then we are going to set it to 20%. So it's going to be around 440, and then to 30%, it's going to be around 500, and then to 40%, it's going to be around 550. So I've set the measurement range for the wavelength from 0.4 to 0.55 because it works for us for this case, and a number of samples of 50 data points. I can increase to 100, but then it's going to increase the simulation time. And then finally we'll plot all of these. There is an angular plot as well, like giving the emission characteristics, the solid angles for the emission characteristics, but I do not excuse me, I do not have the models for three-dimensional simulation, so I'm going to skip this part. And then we are going to plot the ID characteristics, and we are going to look at the power spectral distribution of this light emitting diode structure. And we will also look at the energy band diagram under forward bias. So the simulation is already run. Let us first look at the energy band diagram of this structure under forward bias. So we actually have three structures at 3.5 volts, 4 volts, and 5. It's actually the label is 5, but my simulation is running from up to 4.5 volts. So ignore the 5 volts. I mean, I could have, like here, I could have done 4.5. Forget about the label. So this one is simulated at 4.5. Let me look at one of these. For example, let me look at this structure under forward. So I'm going to delete the rest of them. And these lines over here are actually the current flow lines. How does the current in quasi-vertical devices, they must be flow that flows to the edge in the quasi-vertical device, high percentage of the current, but I'm not going to focus on that part. I'm interested in looking at the energy band diagram at 4 volts. So once again, we draw a cut line in this region, and then left click on this plot on the right, click display. It's showing current flow lines. Disable that, enable the conduction energy level, and the valence energy level, and hit apply. And then we already know the interfaces, so I'm going to disable the stars, asterisks, and the back vertical lines. So here is our energy band diagram under the application of forward bias voltage at 4 volts. Here is our p-type gallium nitride layer, our p-type aluminum gallium nitride layer. On the right side we have our n-type gallium nitride layer, and over here we have the indium gallium nitride quantum well corresponding to a particular band gap. So as I discussed in the close to the start of the lecture, that there is spontaneous polarization in these layers because of strain and lattice mismatching, and then there is piezoelectric polarization due to the application of electric field. The combination of these two result in a compound effect which is called quantum confined Stark effect. So because of that reason, for the indium gallium nitride, this quantum well does not have a straight conduction energy level along the x-axis. It's kind of sloped. Similarly, we don't have a constant energy level for the valence band along the x direction. It has a slope as well. So because of the quantum confined Stark effect, because of the compound effect of spontaneous polarization and piezoelectric polarization, we have band bending in in this quantum well in the indium gallium nitride layer. And because of this band bending, you see that we know that electrons, they have a tendency to move to the bottom of the conduction band, and holes have a tendency to move to the top of the valence band. And in these layers, this point over here, we will have the maximum concentration of electrons is not directly aligned with this layer over here, with this point over here, where we will have the maximum hole concentration because of the quantum confined Stark effect. So that is the primary reason that we cannot have thick layers of indium gallium nitride, because if we grow them thicker, then these points would be farther away from each other, and we will have less probability of electrons recombining with holes in the active layer. So in indium gallium nitride LEDs, in which the active layers are indium gallium nitride, the thickness range is like 2 nanometers to 5 nanometers. In this case, it's in our case, it's 3 nanometers. Then the purpose of this aluminum gallium nitride layer over here is to stop electrons from moving from the n-type layer to the p-type layer, because it provides a barrier to electrons, and it contains the electrons in this quantum well instead of flowing over this barrier and moving to the p-type layer, because we need electrons in this active layer. So that's why the aluminum gallium nitride layer is used, and that's why it's called the electron blocking layer. It helps the electrons to contain in the quantum well, improving the efficiency of the light emitting diode. So forward biasing reduces the barriers. Now it's easy for electrons to flow to the quantum well from the n-type gallium nitride layer, and similarly it's easy for holes to flow to the quantum well from the p-type gallium nitride layer, and they recombine along the energy band gap, resulting in the emission of photons. Here are the IV characteristics of the light emitting diode, simulated up to 4.5 volts. As we know that the terminal voltage for diodes is close to the band gap of the materials used in that diode. In light emitting diode also has a p-type layer and an n-type layer. And this is gallium nitride based light emitting diode. So the turn-on voltage for this is close to the band gap of gallium nitride. Band gap of gallium nitride is 3.4 and its turn-on voltage is approximately it's 2.8, around 2.8 volts. Here we see the IV characteristics. So at 4.5 volts, our maximum current that flows through the light emitting diode is around 103 milliamps. But generally LEDs are characterized at a current of 20 milliamps, for which the corresponding voltage is around 3.25 volts for this light emitting diode spectrum. Now, we are also interested in looking at the peak emission wavelength from this light emitting diode, because I will discuss that a 10% content of indium in indium gallium nitride would result in emission in the close to the ultraviolet light range. So let us look at the power spectral distribution of this light emitting diode structure. And as we can see from here, that our peak emission wavelength is approximately 418 micrometers, 0.418 micrometers or 418 nanometers. So it's close to the ultraviolet light range. Now, I want to show you to see the effect of increasing the indium content in the indium gallium nitride layer and see the effect of that on the emission wavelength. So for example, in this code, let us increase the indium content from 10% to 20%. Our indium gallium nitride there is region number 2, and here we can set the indium content. It's let's set it 0.2, which means 20% indium content in the indium gallium nitride layer, and then let us simulate it to see the emission wavelength for this. The simulation is going to take some time, but we can look at the runtime status of the simulation in this window. Not interested in the dev schematic diagram now. So as you can see now, it's running at 0.5 volts, 0.6 volts, 0.7 volts, 0.8 volts, and so on. Let us wait for the simulation to run completely, and then we will look at the power spectral distribution of this light emitting diode when we have increased the indium content from 10% to 20% in the indium gallium nitride layer, which is the active layer. Now it's running at 3.7 volts, We are getting there. We will be there in a minute. And 2 volts. So now I'm interested in this curve. Let's check the power spectral distribution. From the power spectral distribution plot, we see that our peak emission wavelength is now around 450 nanometers at 20% indium content in the indium gallium nitride alloy. So with increase in the indium content, we are actually reducing the band gap of the semiconductor, and reducing the band gap means increasing the wavelength of the light emitting diode. Now let us look at just one more data point, and after that, let me close the previous one. And keep this one. Simulation, and now let me increase the indium content to, for example, 40% and see the effect of that on the emission wavelength. So now once again we gotta wait for a couple of minutes before the simulation is completed. Reminds me of a proverb, which is that patience is a virtue. In this aging time, everything is running so fast. Patience is really decreasing. So the simulation is running at 1.1 volts. finally we are here. Let us look at the power spectral distribution. Mainly say let's look at the emission wavelength. So now that we have further increased the indium content in the indium gallium nitride alloy, which is active there in the light emitting diode structure, our peak wavelength now is around 533 nanometers, around 530 nanometers, which is in the green wavelength range. So at 10% indium, we were in the ultraviolet emission range. For 20%, we were in the blue emission range. Now at 40%, we are in the green emission wavelength range. Now, going back over here, so in the Silvaco TCAD code, I showed you a light emitting diode structure based on gallium nitride, and the active layer was indium gallium nitride based. But we just had one active layer, one light emitting layer, but there is also possibility of having multiple light emitting diode layers. For example, here in this structure, I have introduced two light emitting layer. One has an indium content of 16.5% and the other one has an indium content of 27%, and we need to introduce a spacing layer between them. Otherwise you would just get a single emission, not two different emissions. And for this structure, here is the layer structure diagram simulated in the Silvaco TCAD software. Here are the layer thicknesses of these of this light emitting diode. Here is the energy band diagram under thermal equilibrium, and here is the energy band diagram under application of forward bias voltage. And then the IV characteristics and luminous power, etc. And then from this structure, which I previously simulated, I found out that at a voltage of 3.75 volts, corresponding to a current of 13 milliamps, I achieved an emission wavelength of around 530 nanometers. Then at 4 volts corresponding to 22 milliamps, I found both blue and green light emissions. But further increasing the voltage to 4.25 volts corresponding to 33 milliamps, the blue light emission was more dominating. And here in this structure, I got blue and green light emissions, but we can adjust certain parameters. For example, indium content and the thicknesses of the indium gallium nitride layers and the spacing layers and the carrier concentrations to achieve blue and yellow light emissions. And we know that the combination of blue and yellow light emission results in white light, which is used in standard lightings. And we can grow more complicated structures in simulate more complicated structures in Silvaco TCAD as well. This concludes the lecture for today, and I will see you next time.